All right, welcome back, everybody, to the Additive Snack podcast. I'm your host, Fabian Byleveld, and today I'm really excited to dive into the high-pressure die casting industry. Again, we recently had a really interesting episode where we talked about die casting and injection molding, but today we'll dive even deeper into the high-pressure die casting industry. Why am I excited? Because we rarely talk about this industry in additive manufacturing. We take it as a given, but it is having a huge impact on many industries, especially on the automotive industry today. And therefore, I'm excited to have Wes Byleveld, the director of additive manufacturing at Exco Engineering, with me. Probably butchered that last name because I'm German and it's a Dutch name, but I'll try my best. But in any case, Wes has a awesome background in additive and in die casting, has been in the industry for a very long time, and is pushing Exco forward and is pushing additive manufacturing forward on a daily basis. So therefore, without any further ado, Wes, welcome to Additive Snack.
Thanks, Fabian. Appreciate you having me on the show.
All right, so let's first talk a bit about you. I think it's I'm sure an interesting position to be in to see the interface of die casting, which is still a somewhat traditional and conventional industry, and to be in that interface to additive manufacturing, which is still mostly seen as a new innovative technology. So what's it like to be in that position of that interface, to see the old and the new, and also how did you get into that interface?
Sure. So I've been with Exco Engineering now for 21 years, minus a few between 2009 when the industry all fell apart there. So I've been there basically 21 years. I started in our die cast department. It gave me a lot of knowledge into making castings for one. So we do die sampling here at Exco on our own machine, and so I was doing process development, robot programming, PLC programming, and from there I kind of transitioned up to more of an engineering role. Just been there for 10 years. So I got into the engineering, worked as a project manager on one single project, designing and building a die for one of our customers. And from there, my boss asked me to start looking at additive manufacturing to see whether it was kind of a industry or, a tool that we could use in our industry. Die casting is a tough industry. The East is really, especially now, like China and things, the pricing coming out for high pressure die casting dies is unbelievably low. So to stay as a high pressure die cast tool builder, you really have to invest into the company. You have to look at different ways that you can compete and produce better dies for your customers, so you can get that premium price in the end. To get back into the additive, so my boss, he looked at additive actually at EOS and a couple others, I think it was DTW or something like that, in 1998. But back then it was a real sintering process. So the laser would sinter the pieces together, and then you have to infiltrate it with a copper alloy of some sort, or copper bronze alloy, and you'd end up with a part. But for high pressure die casting, it just doesn't work. So that kind of, after 10 years, we started looking, and the technology had advanced. We looked at some machines for one to see what the pricing was, but in the end we used a few service providers in 2014, 2013 to see is it something that's actually going to last in production. We had some good successes with our customers, and from there we started purchasing machines. So 2015 we bought our first machine. So it's been a road, that's for sure.
Yeah. Wow. 9 years ago. Yeah. 10 almost.
10.
It is
close.
Basically 2025. And what was your first perception then? Were you surprised that additive could deliver? Did you expect it? The reason I'm asking is there's many of our listeners that are in similar shoes today, right? Where they're exploring additive, they're trying to figure out, is this technology ready for my industry? How did you guys approach that evaluation, and then took the leap into additive?
Yeah, that's a good question. We kind of just jumped in and we said, you know what, let's work. We have some real good customers we've had for 20, 30 years, and they were also interested in knowing a little bit more. I think what it drove down to was, the castings now compared to 20 years ago have gone up in tolerance so much. Leak specs on these castings have gone crazy, really, to be honest with you. Like nobody wants
Hmm.
oil on their driveway anymore. Like their truck doesn't want to, you don't want oil leaks out of your engine or your transmission case. Like in the past, it didn't really matter as much, but now like nobody wants that. So the leak
Yeah.
specs drive a lot of that. The tolerancing, the way they design the castings, it's so complex now compared to the shapes that were once there 20 years ago for the similar type product. Um, so we said, well, let's just put an insert into production. We'll take a crack at putting a conformal cooling line in. But we looked at a really bad section of the casting of an engine block, and it lasted 5,000, 6,000 shots, and we thought, well, without even trying, if we get that many shots out of it, um, it's something that we
Wow.
should probably explore more deeply. So we just really actually decided at that point to buy a machine.
Cool. Yeah, I mean, you proved out the case for a performance increase, right? Where you saw a gap in conventional that additive could tackle.
That's right.
And yeah, it's true. I mean, I have an older car and a newer car, and the old thing still I have stains on my driveway and garage every day.
That's right.
Um, so whereas you looked into additive, Exco still has a very long history in conventional die casting, right? I think you guys were founded in the 50s. How did you then convince the rest of the organization to come along and go with you? Was it data proof points? Hey, we have 6,000 shots and a cycle time optimization, or what did it take to get the rest of the organization to buy in?
It didn't take much actually. Yeah, we've been around for a long time. Like I said, with pricing coming out of China and all these different places of the world, you have to be able to compete on a different level. It can't be cost, it can't be price of the dies. It has to be something more. So it's about performance, right? Um, so that's without adding a new technology or changing technology or automating your existing business by like in our case we're looking at a lot of AI and how do we integrate tooling and how do we get better with cutting steel and all these things, and a lot of it based around automation and everything. So it fell right into place for the long-term goals of the company to say, hey, like this is a tool that we can use that's going to make our customers a better die, but in the end, so every die that we produce for the last maybe 5, 6 years now has included additive inserts in them. But then, like most of the other inserts that we have, and we have 6 machines now, 6 4 laser machines, and most of those inserts actually get sold to the general die casting industry, whether it be tool builders or die casters themselves or injection molders.
Interesting. Okay, that's super helpful to understand. Now, as far as I understand, additive is a piece of the die casting process that is almost at a point of no return, right? Most inserts that benefit from additive, it would be really difficult to go back to conventional. Before we dive deeper into conformal cooling channels and what that means and what that looks like, can you give our listeners a high level overview on what the process of high pressure die casting looks like? What are the key components of such a process?
Sure, sure. So die casting, it's a very complex process in many ways, but also at the same time, it's a very simple process. It's, a customer gives you a part, you look at that part, and you build a mold around that part that it'd be the opposite mirror image of what the actual part shape looks like. It gets put into a large, what we call a holder block. So you machine the component, the opposite of what the casting looks like. You machine the component, yeah, put it into a holder block because of the pressures of the high pressure die casting process are so high. Anywhere from 5 to 15,000 psi cavity pressure. So these dies have to be very large. Based on the parts that we specifically make here at Exco. But even like it's all about the projected area and surface area. Creating how much force or yeah how much opening force that die requires, right? So basically, you have a stationary half of the die that sits in the die casting machine and a moving half um, on the moving side, obviously, and you inject molten aluminum into that die cast mold. It solidifies, the die opens back up, and the part is ejected out of the press, and then that continues over and over and over again, right? So you end up
Mm.
with our dies, they can go anywhere from 60 to 100,000 cycles before rebuilding, and some of the holder blocks, these big blocks of steel that hold the main inserts, they can go up to a million shots, no problem. So it's yeah,
Yeah, crazy requirements
it,
for an additive part.
it is. And
Definitely.
between the
Yeah.
gate, I guess, between the gate velocities and how fast, you're talking 20, 30 milliseconds of cavity fill, to get 100 pounds of aluminum into a die. Like it's an amazing thing. And the die steel cycles from 30 degrees Celsius to 300 degrees. You know what I mean? Like it moves over and like all over the place. So the die steels see a lot of fatigue and wear. And when it comes to the additive parts too, right? Like that was some of the worry about it. Does it fall apart? Well, it doesn't.
Yeah, yeah, super interesting. And then when we talk about the additive components within that process, we're mainly talking about the inserts, correct?
Yeah.
Um, is that certain components still conventionally manufactured, where and then merge a conventional part with an additive part? Do you print the whole insert? What does that split look like?
Sure. So like you'll have a main insert, say, and within that main insert, there's a subsection. Maybe it sees high gate velocities, or maybe it's very prone to heat checking in the steel. So what you do is you sub-insert what they call sub-insert that section out. So out of this large piece of steel, you sub-insert a smaller subsection out of it. Now that smaller subsection, the additive process is quite expensive and the material is very expensive. So you don't want to be building these giant dies necessarily with all additive components, even though we do that. A lot of them are just very much smaller components within that large.
Interesting. So you try to identify where my critical hotspots or challenging geometries that are difficult to manufacture conventionally, and that's where additive then comes in, mainly through cooling channels and other features.
Yeah, I think that I think
I
the
know.
big I think the big one would be like the like I said, with the casting complexities that are there now, you have thin sections and thick sections of casting of aluminum, right? So those thick sections, as soon as you have a thick boss where you have to drill a hole for whatever, holding that casting in the car or to a bracket or something like that, they're
Hmm.
very prone to porosities. And porosity, you can't get rid of porosity with additive, but you could sure move it around a little bit, to help distribute it to other areas of the casting that don't really matter.
Interesting. And you do that through better thermal control then.
Better thermal control, aggressive thermal control. So
Okay.
and
Yeah.
like one of the biggest things is die solder. So die solder is when the aluminum actually sticks to the cavity surface of the mold, and that cavity,
Mm.
so it slowly builds up on that steel. So every cycle that the machine goes through builds a little more aluminum until that aluminum starts sticking to the casting, and you actually tear a piece of the casting out of the casting itself, like a small tear in the casting.
Oh,
And what that does is it opens up potential leak paths between, oil channels, high pressure, or even oil to water channels. So if you can control that solder, that'll allow you then to run more cycles. Obviously, your OE on the machine goes higher, and Yeah, you're not in there polishing all this die steel.
Interesting. I know you have a CAD file prepped that we could take a look at that I think highlights the difference between a conventional insert and an additive insert pretty well. Can we pull that up?
Sure, if you can see that.
Yeah, we can see it. Awesome. And maybe while we talk about it, we should make sure to also verbally explain it for listeners that
Sure.
don't have a screen.
So the part on the right here, so this is part of a larger mold for one of our customers, and it creates the output shaft of a transmission case. So it's where the drive shaft comes out of the transmission case. And you can imagine this being like a bore area that has, say, after machining, has a bearing inserted into it. So that's for the drive shaft. Conventionally made, it's a piece of tool steel. You put this on a lathe, you turn all your features, and you drill a hole through the center of it. And this hole then has what we call like a cascade or a bubbler tube inside there that fountains water into this upper area of this drilled hole, and the heat gets drawn out of the casting into that water line. So yeah, it does its job. It'll cool itself. But the problem is in these bore areas, these machined areas, often they're thick because of the loads of the drivetrain of the car. They can't have a lot of porosity in those areas. So, you can't do anything else on this insert to cool it down further. So on the left now, we show the same insert, but with a conformal cooling line that addresses an area of that piece of steel that can really now aggressively cool, which can help push that porosity just far enough away from that cast surface that when they go in and machine the actual casting, that there's no porosity present. It's just been pushed farther into the casting itself. So, like when you look at it from the top too, it's
Yeah.
this is a very simple example. It gets far more complex than this, but this is very typical of what we do. And it's the same thing. Like if it's solder or die solder, these areas of inserts, maybe not this one, but these areas of inserts, these upper like really sharp corners often build up with a lot of uh, aluminum, and that having this cooling here helps stop that solder.
Interesting. And what would be my alternative? Could I, if I wouldn't do it additively, could I drill holes at an angle and then close them up again, or is this really there's no way to do this at least at the same cost as by going to additive?
Sure. You could drill holes from all which directions. When I talked about thermal cycling and fatigue, what generally happens to a lot of cross-drilled holes very close to cavity surfaces is those cross-drilled holes plugs leak, and then you end up in a
Mm-hmm.
worse situation where you end up with water inside the cavity from leaks on that insert. So, there's so many different ways of potentially doing this as a very small insert. Um, but in this case, it's more cost effective, and they last just as long or longer than the conventional insert to begin with, if you do them out of the additive.
Cool. Okay, so let's talk about benefits for a second. So we talked about reduction of porosity of the cast by reducing the die solder. We talked about I think cycle time reduction.
Yep.
I'm guessing, right? Because I can get the heat out faster, so I have solidification faster. Are there any other benefits that come with that? Maybe even as a byproduct, an accident.
Um, yeah, like I said, polishing related downtime is probably our biggest thing that we solve. So better OE on the machines themselves for the customer, right? So I'll just get into the soldering. So say you run your die 3 shifts per day. You make whatever 30 parts a day. So you could go start figuring your cycle time, and every shift you have to go down for an hour to go in there with like disc grinders and grind off that aluminum off that die cast cavity. So you can imagine, you're down for an hour, so you lost 30 parts per shift, so you've
Wow.
lost 90
Yeah.
parts. And then you have startup scrap because you can't just pump aluminum into a die cast mold and start making good parts right out of the get go. You have like 5 or maybe even 10 warm up shots before, and so those ones get thrown out. So maybe you throw out 120 shots per day,
Wow.
just in polishing related downtime. So you put an additive insert in and help solve that. All of a sudden, you're making that many more parts per day, right? So that's the cost benefit sometimes you have to look at. Porosities as well. Like if you look at porosity, we had a program, this is years ago now, where they couldn't really make the casting without the additive component. They could. The problem was that they would have to do an impregnation process to the casting. So it's basically like after the casting's done, they trim it all off, and then it goes out to an outside supplier, and they get dipped into a liquid that kind of seals off that casting, so you don't get leaks in there. But you can imagine, after casting, shipping it over to this thing, and 30-50 bucks a casting, whatever the cost is of the impregnation process. We were able to take an additive insert and completely eliminate the impregnation process. So, like they were 100% scrap without, but 20, maybe
Wow.
15, 20% scrap even with, at times, like without the impregnation. We got it down to like 5% scrap and no impregnation. So it was a real winner, right? Like, like how you can't even imagine what the cost in a year would be on a million parts, right? So
Yeah. Is I mean, what is really interesting to your cost comment when we first started our conversation, where if we go back to the insert that you just showed, I'm guessing that the conventional insert is probably cheaper to manufacture than the additive insert.
that's right.
How do your customers do that return of investment calculation? Is it then by increased output and reduced scrap, and that then justifies the additional investment into additive inserts? Is it that easy?
It's most of the time it's that easy. It's easier when the caster's having problems with a specific program. When you like as a tool builder or as a purchaser for die casting dies for a casting company, it's all about the upfront cost. Why does this insert cost 4 times or 3 times the cost of a conventionally made insert? No way, we're not going to do this. And we just say, okay, but no, you're not going to be able to make your castings without. But they're driven on the cost, and then it gets into
Yeah.
production, and then it was you already have your backup plan ready, that it's going to cost this much, and sit down with tooling engineers and managers and say, listen, like you're not going to be able to make this casting without these components being additive, and you just kind of work it from there, right? And like I said, our last couple of years, especially, we did a program this year, and it included, I would say, 7 or 8 additive inserts into a engine block program, and the casting's impossible otherwise. Like there is no way of doing it otherwise.
Yeah. Which really also means that additive is not only making the high pressure die casting process more efficient for automotive manufacturers. It even therefore enables programs and designs that wouldn't be possible without additive,
Yeah, absolutely,
right?
absolutely. Yeah, no,
Yeah.
no, yeah. Like when we started die design, the first thing you look at is the solidification of the actual cast component, without even putting runner systems or venting or overflows into it. You get a real good understanding at that point in time already. What are the requirements going to be on this casting, and you can start deciding and start planting the bug. Like, okay, this is how we're going to design the cooling lines. This is thermally, we need this here, and cycle time, we need maybe an additive shop block, or maybe not, right? So it's all about the upfront design and simulation work that for us that really dictates how much additive is going to be in a die.
Super cool. No, I mean, I mentioned this in the beginning. Die casting and additive, it's one of those hidden champions in additive manufacturing that have such a big impact, and we don't really talk about it enough. As far as I understand, besides inserts, there's even additional applications within the die casting process where additive is helping to make the process more efficient or reduce complexity? What are some of those other applications that touch the die casting process?
Yeah, no, for sure, for sure. Like it's amazing when you when you look at like a whatever 4, 6, 9,000 ton tool. There can be literally thousands of water lines. So in the
Wow.
pieces of tool steel, and the component sizes, the die steel sizes are just so large and complex that you could imagine for every hole that's drilled in a what they call a bubbler circuit, a fountain, you have an in and an out line. So that's two rubber hoses, all these fittings, all these leak points. So even if you're 99% sure that you have no leaks, that 1% is still three leaks on a die casting die. And when that die weighs couple 100,000 pounds and it's in a machine and it takes 2 days to replace, three leaks is not acceptable. So, we've come up
Hmm.
with some solutions where we can use additive to create manifolds. So you can kind of gang up certain sections of the water lines. And you could imagine, I can't really show it because it's proprietary, but you could see 5 water lines in a small area that fits within, call it the 400 size printer bed. Um, in that area, you'd have 10 water lines
Hmm.
plus, so you're 20 to 30 leak points already. We can create a manifold that goes over top of these 5 water lines that have one in and one out to create either a parallel circuit or an in-series circuit. So you've reduced your water lines, your overall water lines that are coming out of the side of the die for one, but you're also reducing all those potential leak points because you come up with different
Yeah,
ways of sealing those pipes off.
interesting. Yeah, I mean that's a huge impact. I mean, probably just as much of a risk reduction than the conformal cooling lines, where I have additional operations that I can now get rid of.
Oh yeah, it takes hundreds of hours out of an assembly of one of these large dies.
Yeah, super cool. Um, I'm kind of curious to understand how well additive is adopted in the overall die casting industry. Like, would you say every new automotive program now has a casted part in it that was touched by additive, or do we only see it at the high performance vehicles? Where are we in the adoption curve there?
In North America, it's well. I would say it's well used. It's not used everywhere. You can imagine that there's many more smaller die casting dies and smaller die casters themselves
Hmm.
that will not run it. Like it's just such a competitive business. It's amazing that they're still alive in North America. But when it comes into the larger molds and the more complex, like engine blocks, transmission cases, it's less used, but can be used in structural castings. Um,
Hmm.
we, I, you know, Last year we would have put about 900 inserts into production. So you start thinking about it like that. Yeah, no, it's well used for sure. Most people, once they start using the additive, it opens up their eyes to other areas within their other cast parts. That it's like, wow,
Hmm.
this we
Hmm.
can introduce this over here. Sure, let's put it over here because we have a problem, right? So it's Europe less so. Europe's still
Interesting.
caught up too much in the materials. Everything has to be H11, H13. It has to be that. It took us many, many years to let casters know that marging steel. That's what we mainly use. We have others under our belt, but it's mainly marging steel. And if you heat treat it right and you understand the materials, it's actually behaves just as good or better than all these H series steels, right? So it's
Hmm. Hmm.
once you get that into people's heads, it opens up the industry very quickly because now it's no
Yeah.
longer, oh, you guys don't do H11, H13, we can't use it because it's not a material that we have approved. And once they get that approved in the system, then they run with it.
Yeah, us Europeans can be a bit stubborn, huh? Yeah, for sure. And then, okay, that's interesting. So really, there's still just an adoption challenge when it just comes to specifications of older die requirements really that just nobody is touching them or updating them just because they exist.
That's right, and you know what you realize in the end, once you say this insert works and it saved you this much money, nobody actually cares about the material.
Yeah.
You know, they say, well, what was that material again? Margin steel. Oh yeah, that margin steel works great. You know, that's what it turns into. Opposed to no, it's never going to work. It's never going to work. It's not on our approved die list. It's really interesting to watch them.
Yeah, yeah. Money speaks, huh?
Yeah.
Yeah. Also there. What about outside of the automotive industry? Um, do we see adoption outside of automotive from your perspective?
Non-automotive castings,
Yeah,
or
just in the general casting industry, where additive inserts play a role.
the low pressure, it's like low pressure semi-permanent mold industry. We've done some inserts for all, kind of all over the world actually for that industry, and it's you the requirements of that are not there as much as for the high pressure die casting industry. And like the we talk about the high velocities and metal flow in high pressure die castings. It's really rough on the material in that respect, for wear properties, heat checking and all that. But in the low
Hmm.
pressure industries, it's they put a lot of heat into the insert. So and the casting process goes from like a standard die casting, I call, like, kind of 30 to 120 seconds, depending on what part you're trying to cast in high pressure die casting. Theirs could be 2-3 minutes per casting. So the requirements aren't quite there as much.
Okay.
It's just
Okay.
a completely different industry.
Okay. Interesting. Yeah, I wonder if how changes in the mobility sector are gonna impact that, right? I mean, I know that I don't know enough about it, but I know that the FAA just also made changes to vertical takeoff and landing vehicles. I don't know if they have casted parts in them, but yeah, I'm curious to see how that changes the landscape.
Oh yeah, for sure, for sure. And they talk about, you hear Elon Musk and the rockets, and the way that the space agencies and NASA have been for years, right? Like if they start introducing, say, into castings into aerospace, which are generally, like, you sure there's lots of castings probably in that industry. I don't know personally, but I'm imagining a lot of that would be investment castings and things like that. Whereas high pressure die castings is, like, it's too much porosity, or there's things there. But maybe with additive, who knows, maybe you make better quality castings in the end.
Hmm. Hmm. Yeah, well, we'll see. It stays. It'll be. Yeah, we're just at the beginning of the adoption. What are some challenges that you guys are either overcoming or that you believe still need to be overcome in order to grow the additive and die casting interface even further?
Yeah, sure, there needs to be a bit of a cost reduction for sure. But even materials, like I talk about the margin steel working, and it really does. We go through so much margin steel in a year, it's unbelievable. But you know, I think if material manufacturers were to actually listen to the additive, the guys doing the additive, and come up with, like, material properties and materials that are printable but yet have, a lot of the characteristics of the forged wrought materials that are very good in current production, but are printable, that would really help things out, right? Like, everybody wants H13, but it's not really a printable material, unless you start reducing the carbon in it. And if you reduce the carbon, it's no longer H13. So, like, what do you want to say about it, right? So if we looked at material wise, it'd be great to have more people looking at making more printable materials for the industry. I think that'd be
Mm-hmm.
one.
Mm-hmm.
Um, machines are pretty good. They've been around for a long time. There's a lot of changes coming with beam shaping and who knows all the other technologies that are out there. But you know, our hurdles are, keeping the machines going. Powder supply chain can be problematic for sure. We're good now, but we keep a lot of powder in house because It's just I've toured many atomizers, and you see why we inventory a lot of powder, because you just don't know, and you can't run out
Hmm. Hmm.
once you have customers that rely on you.
Interesting. Yeah, yeah. And as the industry grows, I would also foresee that naturally some of these the market will fix some of these challenges by itself, and probably also innovation and new technologies. Right? You
Uh,
can lower your end part cost by reducing your input or by speeding up your process, just like your customers
That's right.
are speeding up their processes through your inserts. And speaking of innovation, what are you excited about when you look into the next 3 to 5 years? You know, are there certain aspects of the industry that give you yeah, to make you excited?
Yeah, there's so many different, like D is very exciting technology. It's hard to implement as a tool builder. The machines are very expensive currently, and but I think there's
Hmm.
a lot to be had of there, or maybe it's a combination of D and laser powder bed. There's so many things there that that open up possibilities that we don't even know of at this point in time. But the reduction in cost got to be there for sure on the capital itself. As I think we will get there on materials. Material development, and I think as the processes and machines speed up, you might see a complete change where you might not get as much forged materials anymore, and we might be manufacturing whole. Who knows? We might be manufacturing whole dies in within 10 years, being almost all additively manufactured. Right? Like it's kind of sky's the limit, and pushing the limits and understanding the industry is that's more people have to do
Hmm.
that.
Interesting. Yeah. What about on the software side? Do you see uh, automation in design, simulation capabilities having a further impact on how you guys design certain inserts, but also potentially how your customers and your customers are understanding the or unlocking design potentials through downstream die processes.
Yeah, I think I've seen a couple different companies come out with the automated systems of, say, we'll call it waterline design, to specifically put it into die caster injection molding industries. I think they I think there's a ways to go. It's that
Hmm.
typical example of we're going to get water everywhere, and it's going to solve all the issues in your mold. But what they don't realize is when a piece of die cast tool steel is too cold, it causes more problems than the solder itself, right? So anyway, there's so many things there, but I think it'll continue to grow as required. Simulation, yeah, it's key. Like we simulate everything to get an idea of initial waterline placements and things like that. But like it's there's so much out there. There's so much automation that could happen, even in the machines. Like we're highly utilized on our machines. I think there's more opportunity to automate these machines because they can run virtually unmanned for the most part, right? So
Hmm.
pallet changers, which have been around for a long time in the CNC world, I think I could see a lot of robotic control and robotic pallet changing and build changing happening unmanned, which is going to really, that'll really help and change things around.
Interesting. Yeah. Yeah. All industries will not remain untouched by robotics, AI, and other developments. Right? I even think AI is going to have a huge impact on material development. Right? Running similar models like AlphaFold, where Google has, I think they just won 2 Nobel Prizes, maybe even three, on their AlphaFold's AI engine that predicts the folding of proteins. There's a lot of material ally combinations out there that could be simulated
Absolutely.
by some of these tools. So yeah, I think we're still gonna see some really awesome innovations coming out there. Wes, man, it was awesome to have you on the show. I really enjoyed our conversation. I learned a lot about the process, and I thought it was a really cool episode to really dive way deeper into die casting than we have before. So thanks so much for being on the show.
Yeah, thanks for having me. Appreciate it.
And thank you out there for listening to our episode. If you liked it, please share it on your favorite social media, and give us a thumbs up on whatever platform you're listening to. If you have any suggestions on guests or topics that you would like to hear, please feel free to leave a comment or show us an email at additive.snack@eos-na.com. This was this week's episode, and I will see you next time.